Excellent. Thank you very much, everyone, for coming. Thank you to UQCS for hosting this. So about 3 years ago, one of my colleagues presented here, and he presented a linear programming problem, and then his presentation ended before he discussed how to solve that problem. And he told me that that should be the point where I lift up and take off from. So my goal today is to solve that problem and give everyone a basic understanding of how the simplex algorithm works, and hopefully an intuitive understanding of how it works. So you can, if you don't know the precise steps, you could work them out in your head because you understand the problem well enough. I'll be drawing from two really good textbooks. So first one is Linear Programming, 4th edition by Vanderby, and Linear and Nonlinear Programming by Leuenberger and Yi. They're fantastic books. They take very different approaches. And so if you read the first 3 chapters of each, you'll get 2 really good understandings of what I'm going to talk about. So I've worked for a company called Polymathian for about 6 years, just a little bit over 6 years. And so we are an industrial mathematics company. So we solve really complicated mathematical problems using software for heavy industries. That's the sort of elevator pitch of this company. And so it means we get to solve a lot of very complicated simulation and optimization problems. So we have a mathematics side, which can often get very difficult, and then we also have a software side. So we need to give that software to customers as well. So the kinds of problems we solve are these flavors of problems. These are all the same mathematically under the hood. So if you just got an airline with no schedule, someone just gave you 50 planes and 1,000 staff, how do you make sure, how do you run it? How do you make sure your planes come back? How do you make sure your crews are utilized legally? Like, you don't just leave someone in London for 3 months. It's how you come up with all the different schedules that stitch the airline together. How do you know you're going to make money as well? That's another thing. Another example is mining. So if you find gold, so if you buy a mining lease and you do some drilling and you figure out you've got gold underground, how do you get it out of the ground? You could just go left to right, top to bottom, like a grid, but you may just mine dirt for 5 years straight. So you want to make sure you're actually making money the whole time. So that's a mathematical optimization problem. And then sport scheduling. So the NFL schedule is a classic linear optimization problem with papers published every year about how many cores and how many hours it took to solve. The AFL schedule would have been a total nightmare this year, but you have things like which team is playing what other team at what location each week, things like that. They're very difficult problems to solve. So all of these problems that I've described are mathematical optimization problems, and they're fundamentally characterized by 3 components. So every mathematical optimization problem, whether it's a continuous problem or a maths like max fx, blah, 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 has 3 components. It has a set of decisions, the first one. You need to be able to represent your real life decisions as maths somehow. The second one is an objective. So you need some way of saying, if I pick a bunch of values for those decisions, how do I decide that one is better than the other? It could be profit, it could be cost, it could be just adhere to all the rules. You need some way of saying this set of values is better than another, so you can order them and optimize. And you need a set of constraints. So these are equations that restrict the valid set of decisions. So you think of the example of like working out who is going to play at the Gabba in the AFL schedule each week. So you have a variable that represents who is playing on one side, and one solution might be Brisbane, 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 but obviously there's a rule that says they need to play home, away, home, away, home, away. So you've eliminated the set of decisions where you just repeated Brisbane over and over because you have some rule that forces you to alternate being home and away. That's an example of a constraint. So if those three components are all linear functions, then you're in the territory of linear programming. And linear is anything that looks like that. So real numbers multiplied by your variables, where the highest power is 1. So you're not allowed things multiplied by each other. You can't have x times y. You can't have sine. You can't have anything else. You can only have linear functions. And by programming, we mean scheduling. So not programming as in computer programming. So this field was developed in the late 40s, and they meant programming as in you have like a gym program, like a schedule, something like that. So it's a weird name, probably an unfortunate term, given that programming has taken off in another dimension, but we do what we can. So I'm going to pitch and work through in a lot of detail the problem that first introduced linear programming to me in probably 2011 when I did Math 3202 at this university. And it's a problem we all have at some point, which is how do you run a cake stand? So the fundamental things I have are I can make cakes and brownies. It's a pretty pathetic cake stand, but I can only make those two things. I have 4 kilograms of flour and 3 kilograms of sugar. That's another thing I have. If I make one cake, it needs half a kilo of flour and a quarter of a kilo of sugar. If I make a tray of brownies, which each has 3, I try to find something that would work with the correct dimensions. So a tray of brownies, which has 3 in each, needs 100 grams of flour, 300 grams of sugar. So each tray, each brownie I sell for $3, and I have 3 in a tray, so I get $9 per tray. And I can sell a cake for $8. So it's a really basic problem, but we can go into a lot of detail with that. And many, many problems, in fact, all problems look basically the same when expressed in linear programming terms. So we can represent that as an optimization problem. So number one, I need decisions. I need my 3 components. My decisions are, I'll let X be the number of cakes I make. I'll let Y be the number of trays that I bake. So I've captured my decisions quite easily in those 2 variables. I have an objective. So the objective of this cake stand is purely capitalistic, which is to make as much money as possible. So my objective is going to be purely the money I make. I've already got those ingredients, so I'm not including them in the cost of ingredients or anything like that. So it's going to be $8 times the number of cakes I make, plus $9 times the number of trays of brownies I make. I'm also assuming that I can sell everything I make. I then need restrictions on those variables. I need to represent the constraints somehow. So I have a flour capacity that I need to respect, which is the amount of flour I use has to be less than or equal to 4 kilograms. So it's 0.5 times the number of cakes plus 0.1 times the number of brownie trays that I make. That has to be less than or equal to 4. So that represents my flour capacity. I have the same for sugar, but different coefficients, so quarter of a cup and 300 grams. Quarter of a kilo and 300 grams has to be less than or equal to 3. So I've got my used sugar on the left, the amount I have on the right. I also have silliness constraints that I can't make negative brownies and cakes. I cannot be paid to destroy cakes, is what that means. They're not always that obvious, and some variables you'll want them to go negative, but that can get a little tricky. So they're called bounds. So we have there a subset of constraints. So if we just keep the core components of that, we're left with this representation. So I have a function I'm trying to maximize, 8x plus 9y, subject to those 2 constraints, my flour capacity and my sugar capacity, and bounds on those variables that restrict what they can do. And remember, linear means everything looks like that, which everything in this problem does look like that. I have no products of variables. I don't have x, y, I don't have sine x, I don't have x squared, anything like that. So everything here is purely linear, and that means I have a linear program. So this representation of the problem is called standard form. The form where I have my linear objective subject to my constraints and my bounds below that. That is a devastatingly important principle in linear programming called standard form. So the 2 textbooks I've referenced have almost the exact representation I have there. So we can see in Van der Bay at the top, we've got maximize some linear function subject to less than constraints in their representation, which I have here. And then I have the restriction in standard form that my variables are positive. So if I have variables that need to be negative, I need to multiply them before I can get them into standard form. Lundberger and Yi has a similar representation, but they have equality constraints, which we'll get to in a second. We'll show that they're actually the same. So representing the ability of an insane number of real-world problems to be represented in that standard form is why linear programming is so powerful. It turns out that basically everything is linear or can be turned into something linear with an approximation. And that part of the sort of art of linear programming is taking problems and working out how to shape them into a standard form representation. And that is so important that there's books that are dedicated to just building models. That book has nothing to do with solving it. It's just how do I take really common problems. So they've got problems there like food planning, manufacturing, factory planning, manpower planning. What else have we got? Farm planning, mining, curve fitting. So regression is a linear problem. Share market design, tariff rates, hydropower. The common problem, three-dimensional noughts and crosses. Optimizing constraint distribution, car rental, milk collection. So there's all kinds of problems that come up all the time, can be represented in linear form, in standard form. And this is the middle part of this book. This book has 6 sections, I think. It's very important. So back to the maths. So we can look at the constraints we have and plot them on an XY plane because we only have 2 variables. So if we look at our flour capacity constraint, we've got 0.5x plus 0.1y less than or equal to 4. I cannot deal with inequalities in my head, so I always need to rearrange them like I did in high school. Get negative 5x plus 40. We can graph that in terms of y and x. So we've got brownies, the number of brownies I make in the vertical direction, and the number of cakes I make in the horizontal direction. And then I can sub in 0 and work out that 0 satisfies this equation. So 0 is less than or equal to 40. So it means 0 is on the good side. So I can say anything in the red zone is good, is a valid use of flour, basically. I can't be out here because I use too much flour. I can do the same for my sugar constraint, but I end up with a lower gradient, lower negative gradient in terms of x, and a lower intercept. And again, I can sub in 0 and realize that I'm interested in points below that line are valid points. Above that line uses too much sugar. The don't be silly constraints force us into the top right quadrant. So I've eliminated anywhere that x is negative, y is negative, or they're both negative. So I'm forced to be in the top right-hand quadrant for this problem. We need all of those things to be true at the same time. So if I make some number of cakes and some number of brownies, I need to adhere to all those constraints simultaneously. I can't make cakes and not use flour, and then later care about flour. So we can plot them over the top of each other, and they are starting to define a region in the XY plane that is what I would consider where all the valid baking strategies are. That's the term I'll use from now on. So that region looks kind of like this. So it's convex, it's got straight lines on the outside, and so anywhere within there is a valid baking strategy. I'm not making negative cakes, I'm using the appropriate amount of sugar, I'm using the appropriate amount of flour. So we can test out just some random baking strategies for feasibility. So if I head purely into the top left-hand corner, where I have 2 cakes and 10 brownies, so I'm at like 2, 10, then I end up needing 3.5 kilos of flour, of sugar, sorry. And so I'm clearly out of my sugar region, and so I break my sugar constraint. If I end up with that strategy, I'll run out of sugar before I finish making. If I'm in the bottom right, where I'm making 9 cakes and 1 brownie, I need 4.6 kilos of flour. And so I bust my flour constraint, but we can kind of see that because I'm outside of the red region, which is flour feasible region. And if I just pick a random point in the middle, so 4,5, 4 cakes, 5 trays of brownies, I'm good. I need 2.5 kilos of each, and I have some left over. So my feasible region is okay so far. So we can also graph the objective function we have. So since we have a spare dimension lying around, we have x and y pairs, and we can just go how much money did that pair make. So for every number of brownies and cakes I make, I can work out how much money I would make. And so this is a flat plane that passes through 0. So if I don't bake anything, which is my strategy right now, I don't make any money. And so it's a plane that increases slightly faster heading in the brownie direction. It's got a gradient of 9 with respect to y than it does in the x direction. It's got a gradient of 8 in the x direction. So a perfectly flat plane. If I just keep going in the distance, I'll make infinite money, but I'll need infinite ingredients to do that. So it's perfectly flat. So again, look at it from the side, very flat. Flatness is very important. It's linear, very important. We'll get to that in a second. So on top of this, we can overlay our feasible region. We can put that underneath. And so we can start to get an idea of what areas do I need to be in terms of my objective? What's the maximum amount of money I could think about making with different combinations where I start to bump into my ingredient limits. There's another view there from the top. These kind of views are really common. If you read the first 3 chapters of those books, they'll all have pictures like this analyzing the interaction between your feasible region and your objective function. So where do we think we're in the feasible region qualitatively is our highest point? People here can answer. Like where are we going to start looking for our maximum amount of money? Anyone here know? Looking at that? Yeah?
It'll be on one of the edges.
Exactly. So we're going to be looking at the edges because we're just going to keep going and making more and more money until we run out of one ingredient. We're going to head in some direction. We're going to run out of flour, and that corresponds to some amount of money. Or we're going to keep going in the sugar direction, and we're going to run out of sugar first. So we're just always going to be moving away from origin, making more and more money until we hit a boundary. So that red line is kind of the area we're interested in, where we're using ingredients and making money at the same time. We would want to go infinitely far if we could, because we could make infinite money, but this red line stops us, basically. We want to head away, but we get stopped by that line because we run out of ingredients. Can we be more specific about where our maximum value will be? So think about if we kept moving further and further away and we hit one of those lines, we could look left or right again, and we could move to the corner at each side. So if I keep walking and I run into one of those blue lines, since the objective is linear, it will either go up in the direction to my left or down in the direction to my right, or vice versa. Or it will be perfectly aligned where the objective will be the same in each direction. So it might be that I make 90 if I head to the left and 90 if I head to the right, but intuitively, that curve is not gonna, that flat plane is not gonna perfectly align with one of my edges, and so I'm gonna be able to keep going on one direction and end up at a vertex. And so if we look at the vertices there, we've got one, if we make pure brownies, we end up with $90, but imagine you were standing on that line. You could see the objective increasing away from you by making more cakes, so you would end up at 93.6. But if I started and headed in the cake direction, I could start making brownies and make heaps of money. So by the fact that the plane I'm looking at is perfectly plane, is perfectly flat, and the corners are where my objective is maximized, I only really care about the corners. So the fact that the maximum or minimum values are going to occur at the corners, we also note that 0, the lowest point is at 0, another corner. So this idea is really important, extremely important in fact. It's the fundamental theorem of linear programming. So yeah, the textbooks didn't have quite a pithy statement. They used too much linear programming terminology, so I had to use Wikipedia. But basically, if you have a convex region and you have a linear function over the top, the maxima and minima occur at the vertices, at the corners. Furthermore, if an extreme value occurs at 2 corners, so if we had 90 and 90, then 90 is also the same along the line that occurs between them. So that is the fundamental theorem of linear programming, extremely important. You don't get to call many things the fundamental theorem. Okay, so do we even care about baking options anywhere that's not a corner? Like, if I just started in the middle, I would have, like, why would you stop baking? If I started in the middle and I had spare flour and spare sugar, you would just keep going until you ran out of one of the ingredients. So I don't actually need to care about any of the interior points if my objective is linear, because I know I can always move in one direction, consume more ingredients, and make more money in the process. You can imagine if the objective was a dome, so if it was like x squared plus y squared, then I could conceivably have a maximum like in the middle of the region if I was standing directly under the peak of the dome, and therefore moving in any direction would start to decrease the amount of money I make. That's where you start to need interior points and taking gradients and stuff like that. In a case where the objective is linear, you don't care. Or you care about other corners, the vertices. So that is a fantastically powerful discovery. It means I now have a finite search problem. My optimization problem is now a search algorithm. I just need to find all the corners, evaluate them all, and pick the one that's the highest. That's the incredibly powerful part of linear programming, why it's called the fundamental theorem. So the terrible news is that there's a huge amount of vertices to look at. So it's actually a combinatorial problem given by that expression. An exclamation point is never good in maths, never good when you're designing algorithms either. So in the case where it's really small in this 2x2 problem, we can literally just graph it and work it out. But the goodness of that approach dies very quickly. So if I had a cake stand with 6 products and 12 ingredients, I would have 2.7 million vertices. So you just get decimated instantly as soon as you step away from 2 or 3 variables and 2 or 3 constraints. But we know to solve the problem, we just need some way of finding and describing vertices, and we'll be okay. So there's one thing we need to note, that is the current way we're representing the problem doesn't actually capture all the decisions we are making. So when I make X and Y of those products, X cakes and Y brownies, I'm also deciding not to use some amount of ingredients. So there's actually like a second layer of decision that's sitting underneath. And so these only exist for each constraint. So the inequality in the top constraint lets me leave flour behind. It lets me not have the left-hand side equal to the right-hand side. And so these inequality constraints imply another decision, which is how much I left behind. So we can add variables that represent how much I left behind of each of those ingredients. So I'll say A is my spare flour, B is my spare sugar. They have to be positive, and then I slap them into the constraints and turn it to an equal sign. And so now that means this constraint is now my total flour or sugar constraint. What I used plus what I didn't use equals my capacity. So I no longer have a less than anymore. That's very useful. They're called slack variables in linear programming. So if we look at the slack variables for our previous examples, so if I'm sitting right in the middle, I have spare sugar and I have spare flour. And so in that particular case, my A is 1.5 kilos spare, my B is 0.5 kilos spare. So those variables are non-zero when I'm in the middle. So we're not touching any of the edges, we haven't run out of any ingredients, so those variables aren't zero. If I look at the top left, so I've got flour left, but I don't have any sugar left. So my slack variable at that vertex, my spare sugar is 0. If I go to the bottom right, so 8 cakes, 0 brownies, my slack variable for flour, my spare flour is 0, but my spare sugar variable is 1 kilo, because I've run out. I'm sitting right on the edge. At this vertex in the middle, at the intersection of my flour capacity and my sugar capacity, and therefore my spare of both is 0. So that's, in this case, the slack variables are 0. So we can look at those vertices in tabular form and just look at them. So I've got my vertices A, B, C, and D, and I can just look at all the variable values for those vertices. So in the first case at origin, I'm making 0 cakes and 0 brownies, and therefore all my ingredients is soaked up into my slack variables. It's basically the left-hand side 4 or 3 has to go into the variables because the others are 0. And then I move around and we have different variables being on and off. So what do all these rows have in common? Does anyone here point it out?
They
What is it?
Zeros.
They have 2 zeros. Exactly. So every row here has the same number of variables set to 0. That's really powerful. That's a really important statement. And the other numbers in each row just come from solving our constraint equations. So when we have 2 zeros, we sub them into those equations, and we calculate the other 2 that are left over. So that's an example there. If I have cake 0 and 0 leftover sugar, I can substitute into the equations and get y and my spare flour. So I'm not in trouble by setting some variables to 0. So this is really powerful, because it means now I've got this idea that I can completely describe a vertex by just setting pairs of variables to 0 and calculating the rest. Like, I have a non-geometric way of finding vertices. I could give you a generic problem and say find the vertices, and you could just do every combination of zeros, calculate the others, and you would have described the vertices. That's really important. So where does the 2 come from? Well, I had started out with m constraints and n variables. I added a slack variable for every constraint, for every n. So I was left with m plus n variables. I know how to solve a system of equations that has the same number of variables as equations. So I've got n plus n variables and n constraints. I can't change the number of constraints, so I need to get rid of the n. So I set n variables to 0, and I'm able to solve the system. So in general, the number of variables you have to set 0 at a vertex will be equal to the number of original variables in your problem. So my number of cakes and brownies were my original variables. And then I'm left with a system that I can solve. So the term basis is used to describe the variables that aren't 0. As soon as you open a linear programming textbook, page 1, they're going to hit you with basis, the idea of a basis. So I have basic variables are the ones that aren't 0, the cool ones, the ones I'm interested in, and then non-basic variables, the ones that are set to 0. And that's the terminology I use. So basic means non-zero, basic means non-zero, non-basic means 0. And you can think of them as like dependent and independent. I choose to set some variables to 0 independently, and I calculate the other ones. So each vertex is also called a basic solution, because it represents a possible solution to our problem, since we know the solutions are at all the vertices. I won't go into where the term basis comes from, it's really complicated. So if we just naively pick groups of zeros, we end up with really bad solutions. So if I just go, okay, I'm going to set cakes to 0 and spare flour to 0, I end up with 40 brownies, but I end up with -9 spare sugar. So I end up busting my sugar constraint by naively picking zeros. It sounds cool, but we've sort of left out the bottom part of our problem, which was the non-negativity restrictions on our variable. So far we're purely dealing with the constraints and the objective. By picking zeros randomly, we end up just ignoring our non-negativity requirement on our variables. So we end up finding too many infeasible variables, too many infeasible solutions that way. We are only interested in what are called basic feasible solutions, BFS. You'll see that initial in the textbooks everywhere. So we want to stay in the region. We can't just be picking zeros, picking vertices outside. So being in that region means that our slack variables are non-negative. They're sort of equivalent statements. As soon as I head out of that, I've broken a constraint and I've used too much flour, too much sugar. So we got lucky because we know that baking nothing is feasible. That may not always be the case. So we can start at that point and then move around and see if we can see if we can find vertices by moving around. So if I start at A, I'm at the origin, I'm using my current strategy of doing nothing. The first thing we can do is make either X or Y positive. So we've also got this idea that 2 variables need to be 0, 2 variables need to be non-zero. So if I've got 2 that are 0, I have a choice of picking one of them to make it non-zero. And so the one I'm going to pick to make non-zero first is probably the one that's going to make me the most money. So if I start making Y non-zero, I'm going to earn $9 per Y, whereas if I head it in the X direction, I'm only going to make $8. So I'm going to just pick the variable that maximizes my objective straight away. And so I'll start moving in the Y direction. We want Y to become positive, which means enter the basis. Sadly, that means I need to kick someone out. Right? Only 2 variables can be positive. non-negative I should say, and two variables have to be 0. So I need to kick someone out. So we need to find someone to kick out of the basis and make 0. So if we keep increasing y, we have to stop when we run out of sugar. The first thing we're going to run out of is sugar. We're going to hit that blue line. So therefore, my sugar capacity is what puts the tightest restriction on my initial baking strategy. I've still got heaps of flour left at that point, but I run out of sugar first. Running out of sugar means A equals 0. I have no spare sugar. So therefore, I've got the option to just kick out A. A is going to become 0, Y is going to become non-zero. So that the choice of variable that leaves is the one that restricts your variable the most. So I'm going to do that swap. That is called a pivot. The idea of exchanging one variable in and one variable out to move to a new vertex is called a pivot. Again, a term you'll see everywhere. You'll see it in logging of engines, all kinds of stuff, of computations that are happening, of solvers that are implemented online. The term pivot is used. So I've gone from my origin, I've pivoted brownies in, and I've pivoted sugar slack out. So I know I've got 0 for B and 0 for X. I can use my constraints again to calculate the other numbers. So I use up a little bit of flour in making the 10 brownies. And so I can update my other values in that row as well. And this is a vertex. This is a perfectly valid vertex. So it adheres to all of my restrictions as well, which is non-negativity in all my variables. And I can also calculate my objective at this point, which is $90, because I'm only making 10 times $9 for the brownies. So can we make more money? We are at this point where we've made 0 cakes and 10 brownies. So again, I can think of it purely from that someone becomes positive and someone becomes 0. I can increase my objective by making X non-zero. X is in my objective. I have to pick that variable. I'm not going to set brownies back to 0 again because that will decrease my objective. So I'm going to go, cool, I'm going to make X non-negative. I'm going to start increasing that. So then which one leaves the basis? Brownies or spare flour? Again, I'm not going to make brownies 0. So I'm going to let spare flour leave the basis. The choice there is pretty obvious. So my flour is going to leave the basis. My cakes are going to enter the basis. And again, now I know that I've got A and B equal to 0. I can calculate the other values. I can calculate how many cakes that gives me, and I can calculate how many brownies that gives me. The other values just get updated based on our constraints. There's no issue there. And I make 93.6. So that's where A equals B equals 0. So in that case, I have used all my ingredients. So can we make more money? Can we make more money? So the requirement is that one of the variables that are 0 becomes non-zero. That's one of the requirements. And so here I'm left in the position that the only variables that are 0 represent spare ingredients. And so making them enter the basis would mean I start entering a baking strategy where I'm leaving ingredients behind, which doesn't necessarily make sense. If we also look purely from our objective, A and B are not in our objective function. I earn no money for having them left over. So therefore, almost by definition, we have the optimal solution. There is no variable I can pivot on anymore that will increase my objective further. That means we have the optimal solution. So that is known as the primal simplex algorithm, those basic steps. And the steps are, 1, we represent the problem in a standard form, which can be challenging but rewarding. We add slack variables, which means we convert the inequalities to equalities, chuck some variables in. We find an initial basic feasible solution. That can be very difficult, but there's another algorithm you can do to find that out. Then we select a variable to enter the basis. And so this is the variable that increases the objective the most. It's max of your objective, argmax of your objective, the variable that has the highest coefficient in your objective. If none exists, you have the optimal solution already. you have to then pick a variable that exits the basis. And that is the variable that imposes the tightest restriction on increasing the variable that you want to put in the basis. So which constraint do you run into first as you start using the variable that you've picked to enter the basis? If you don't pick that one and you pick another one, that one has to become negative when you pivot, which violates the rules. So you have to pick min of the bounds that are implied by that variable. You do the pivot, so you swap them over and you recalculate all your values. You recalculate all your other variables based on those now being set to 0. And then you repeat steps 4, 5, and 6 until you can't go any further. That is the simplex algorithm. It's an extremely elegant algorithm because it lends itself to computational implementation, because it's very, very basic steps that are just argmaxes on matrices, rotating values, updating things. So the steps of that algorithm have pretty much remained the same since 1947. So applied linear programming, identifying that these models are somehow special or interesting, was done in the USSR and by Kantorovich, and he published his work, but no one cared, sadly. And then Danzig was using it during the war, and then started publishing his work after the war, and it really took off. That was in the US. And so the simplex algorithm was first used in 1947, but published in 1951. That algorithm scales extremely well to problems with millions of variables and constraints. But the problem you run into is memory. So if you try to represent a matrix, if you try to represent one of these rows and you have millions of variables, you don't need a representation of every single variable. All you care about is the basis, the ones that are entering and the ones that are exiting. You only care about the delta each time. And so most of the modern implementations, or even the revised simplex algorithm, as it's called, take advantage of sparse matrices. So they don't just compute this giant matrix over and over again, because it could be massive, and most of it is going to be zeros. So this approach also lies at the basis of a huge amount of other types of analysis, known as integer programming, binary programming, and mixed integer linear programming. So other classes of problems. And so they end up being solved. So if you add the restriction that, for example, my cakes has to be integer, so no one is yet to complain that they have to make 7.2 cakes. But we might say, well, we want that to be an integer decision. How are we going to do that? Well, we're going to solve the problem we just solved. We're going to realize we need 7.2 cakes, and then we're going to split the problem into 2. And we're going to add a constraint to 1, that is my cakes has to be less than or equal to 7. And we're going to add a rule to the other problem that they have to be greater than or equal to 7. Greater than or equal to 8, sorry. So then I solve those 2 sub-problems using the simplex algorithm. So I end up being able to solve an integer problem by making many, many, many children linear problems and adding more and more constraints that ban the decimal, ban the fractions. So your speed of your simplex algorithm is extremely important, because you'll probably end up doing hundreds of thousands of pivots when you're solving a big integer problem as well. So we recap our steps. This is basically the first few chapters of a linear programming textbook. So representing the problem in standard form is super important and can be very, very difficult, but very, very interesting, because you need to make sure you aren't dividing variables by each other as required by averages and things like that, or proportions or blending and things like that, which come up all the time. You can't multiply variables by each other. They all need to be separated into linear terms. That can be very challenging. So the fact that everything is linear, or our linear constraints, the fact that all the constraints are linear, mean the feasible region has straight lines on the edges. So you could imagine I could have like a recipe that uses a square amount of flour. So the more cakes I make, the more flour I need non-linearly. And that would mean that one of the edges of that feasible region would be a bulging curve. That doesn't happen. In this case, I end up with pure straight lines and I get a nice feasible region that's convex. because the objective is linear, it means I only need to care about the edges, about the vertices in particular. So again, remember the idea that if I had a quadratic objective, my maximum amount of money might be in the middle somewhere, in the middle of a dome. But the fact that it's a flat line means that I can just keep heading towards an edge, then go left or right and find a really good value. Then I can sit at that value and go to its neighbors if they're good as well. The vertices in the problem are characterized by combinations of zero and non-zero variables. That's a crucial point. That's the basis, the idea of a basis, the idea of variables being basic and non-basic. The idea behind that is you can completely describe a vertex using that really simple approach. Then once we had a feasible vertex, we can just move to an adjacent vertex by picking a variable that will increase our objective and kicking out the variable that restricts us the most. So we just find one and we keep moving to our neighbors until we get to the best one. So that process is guaranteed to find us the optimal solution. So there's a few things we also haven't looked at yet. So finding an initial solution can be really difficult. So imagine if mum says, oh, your grandma wants a cake tomorrow. So x has to be greater than or equal to 1. Damn it. Now my origin isn't valid anymore. I can't just not do anything. When I wake up tomorrow and run this cake stand, I have to bake something. So that has ruled out my origin. And it means now finding an initial solution may be non-trivial. We have an approach we can use to solve that. We haven't talked about infeasible problems. So problems where there is that region, there is no feasible region. The constraints overlap each other in a bad way. And it means there is actually no solution that adheres to all of the constraints simultaneously. That's bad. I may have an unbounded problem. So imagine if I introduce another ingredient like eggs, and I could make fried eggs, and I had unlimited eggs. Then I can just keep making more and more fried eggs and selling them, and I will never hit a constraint. There is no slack variable that becomes zero. Therefore, I can just head in one direction and make as much money as I like. So there's an interplay between infeasibility, unboundedness, and the slack variables not imposing a bound on that variable. I can run into the issue of cycling as well, which is where I just keep pivoting forever because I keep pivoting on the same variable. I kick someone out, they want to enter again. I kick someone out, they want to enter again. And there are theorems. There's actually a really elegant solution to that problem, which is you just pick the variable with the lowest subscript when there is a tie, and turns out that that makes it guaranteed to solve, which is still unbelievable to me. Purely based on the subscript of the variables you use. And we already discussed the idea of 7.4 cakes, which might seem ridiculous. As I said, the integer aspect of it is a basic addition. I just start making sub-problems where I ban the integerness and add more and more constraints. And eventually I'll find a solution to one of my linear problems where all the variables are integer, and therefore I have an integer feasible solution as well. So the way you can find an initial solution is also really elegant. So what you can do is you can say, I'm going to take my original problem and I'm going to solve a really similar problem, which is I'm going to add a variable, the same variable, to every constraint. So I'm going to add a new variable, call it x0, just some other variable that I don't have. I'm going to add it to every constraint. And I'm going to minimize that variable. That's all my objective is, minimize x. And x is added to all my constraints. And so what I'm basically saying is, what is the minimum amount I need to change this problem for it to be feasible? If the minimum amount you need to change every equation is 0, then your original problem is feasible, right? If that variable is not 0, it means you needed to destroy your equations by some small amount to make it work. So all you do is do a phase 1, which is where you minimize this one variable. That always has an initial solution that's valid of 0. We don't run into the mum wants a cake problem with that variable because we just made it up. We can solve that phase 1, and the optimal solution to phase 1, if it's non-zero, means we're cooked. We have an infeasible problem. If the minimum amount we need to destroy our problem is 0, it means our original problem is feasible and we can just keep going. We just swap our objectives and keep moving. So that's a really elegant solution to that problem. You'll often see that described as a phase 1 and a phase 2 approach to the problem. So that is a very, very quick, hopefully intuitive summary of some really foundational and really important topics in linear programming. So the idea of a basis, the idea of linear objectives, the idea of vertices being described as a basis, and the idea of we could just iteratively choose vertices and adjacent neighbors, and eventually we're guaranteed to get the optimal solution. That's really powerful. Thank you. Does anyone have any questions? Yes?
So you said you want to approximate nonlinear programming problems to linear programming. You'd probably use something like sequential linear programming, right?
Yes.
So what sort of guarantees exist that sequential linear programming or something similar would converge onto an actual optimal solution? And what are the benefits compared to like a nonlinear programming solver like SNOT or IOPT?
Yeah. Yeah. So the reduction, as soon as you lose your guarantee of optimality from a practical perspective, you start heading into dangerous territory. So we get approached by lots of people that go, can you solve this weird and really complicated problem? And we don't know if they are also going to 5 other companies and saying, can you solve this weird and uncomfortable problem? But it happens. And so quite often we will get put in like a bake-off against other companies. And they'll give everyone the same set of data and go, whoever comes up with the best solution gets the job, gets the project. And so in that case, you let go of optimality, like at your peril. Because if you know you have the best answer, you can only tie with someone else that has the same approach as you. So you will do what you can to linearize everything. So quite often you'll try to separate, you'll do a separable approach where you'll try to pull apart equations or nonlinear terms and multiply them or add them in with binary variables. So you can bisect or make disjunctions where you have a binary variable that represents, do I do this or do I do this? And so you can even still cram in nonlinear things, even non-convex spaces, by just putting an or in them, which can still reduce down to linear. We don't actually end up doing too much nonlinear programming, purely because we lose the ability to really understand the solve time. There's another one as well. So when you have the simplex algorithm operating, specifically an integer programming approach, you know how far you are from optimality. You have the difference between linear solution and integer solution. And so stopping it is okay. You know if you're 1% away, you can stop it. You know if you're 5% away, you can stop it. But as soon as you start heading into the nonlinear area, you are at the mercy of the implementation of the solver you're using. And you may not know how long it's going to take. Whereas you have some measure of progress if you're using an integer solver or a linear solver. And if you don't know your optimal, you can get some really hard questions from clients. Where like, is this good? Or if you click the button again, you get a different answer. That's really bad because you had some kind of randomness in your problem. So the fact that it's just a raw calculation that always has the same answer is super valuable commercially as well. Yeah.
How often are you guys running linear programming online versus sort of an offline cloud type solution?
Yeah, so all of our deployments are online through AWS. So we have basically giant cloud machines that we create on demand, install our entire stack on them in about 30 seconds, and then solve using Gurobi, Simplex, whatever it is, crunch the numbers, and then the machine gets destroyed and the solution comes back. So we're either going to be typically bound by memory. Sometimes it's CPU. Sometimes the problems are just massive, and so you could still solve it on like a 12-core machine, but you need 200 gig of RAM just to hold the problem. Because when you start doing a binary search with the integer restriction, you need an entire copy of the problem at each node, and so your memory just explodes, basically. Yeah.
Have you guys tried to distribute the problem to like multiple computers? Or?
We have, so you can only distribute the MIP side of it. So the simplex algorithm is extremely non-parallelizable. You can't tell other people to explore the other half.
Yeah.
So the simplex algorithm itself is non-parallelizable. It's purely core frequency.
Yeah.
But when you start to get into the branch and bound tree, yes, you can parallelize that. And you can even do really naive things like just shotgun approaches, where you solve the same problem in 6 parallel systems with different settings in them, and just take whichever one comes back first. And a lot of the solvers will do that under the hood themselves. Yeah. Any other questions? Yes?
You said that the simplex algorithm explores vertices and it was efficient, but also that there were on the order of factorial vertices.
Mm-hmm.
Does this factor into the asymptotic runtime of simplex algorithm?
So the mean complexity, so you can generate random problems. And I think you end up, the worst case complexity of simplex is, so if you look at the pure number of vertices, you end up with that factorial combination. You're only interested if you guarantee the algorithm doesn't cycle, which you can. You never visit the same node twice. And so you know you will at most visit the number of basic feasible solutions there are. So if you know the number of basic feasible solutions there are, which you can calculate, I don't have the expression off the top of my head, and you know you never visit them more than once, then that is your complexity, the worst case complexity. It's something, off the top of my head, it's like n squared, something else, I can't quite remember. So you end up with, it's still bad, but it's extremely usable. And that you actually end up not visiting that many vertices, actually. So you can solve a lot of problems with a huge number of vertices in like 10 pivots. Because you're always heading towards the optimal objective. So the average case, and it hasn't actually been proven to be the complexity you get when you randomly simulate problems comes out to a certain number. No one's actually proven that that is the case yet. But the fact that you're always heading in the right direction massively reduces the practical runtime of the algorithm. You don't end up usually being really close to the worst case. There's a really pathological case called the Clee-McKinty case, which is a model deliberately created to shaft the algorithm, to make it as bad as possible. And it has like horrific runtimes. And you're essentially optimizing like hyper thin regions. So the directions you move in are really bad. But the fact that you're always moving in the right direction means you usually don't end up visiting that many vertices. You also have the recent improvements in the algorithm, also recent, the last 70 years, mean you have many different ways of picking the entering variable and many different ways of picking the exiting variable. And they're called cost strategies or pricing strategies. So you may have a number of variables to pick that enter your basis, and you may not always necessarily pick the maximum one. And when you have variables that are exiting, you have many different ways of, they call them pricing. So when you evaluate their price and pick the best one, use different methods, they can also massively impact the runtime because they're essentially the direction you choose to go in. And so you can tune them for the specific model or type of model you have. So the genericness is the power of the simplex algorithm, which is you can represent all of these weird problems in that one format and then take this basic algorithm and you can sort of plug in different modifications to it, which people have done. But the fundamental steps stay the same. Pick a point, move in a direction.
Yeah, that makes sense because I think from what I remember of Math 3.2, linear programming is actually polynomial time.
It is, yeah.
As opposed to integer programming, which is empty.
Which is tough, yeah. Yeah. Yes, we spend a lot of time at work waiting for integer programs to stop. Or devising clever ways of stopping them. And then you can do a lot of things like use other algorithms to come up with initial solutions, and you give the MIP that solution and go from here and see what you can do. There are a class of problems that are really hard to find a feasible solution, and class of problems that are really hard to prove that you have the best solution. And so you'll use different approaches to solve those different problems. Yeah. Any other questions? All good. Well, thank you everyone for your time. I hope you learned something. I hope you have a fundamental understanding, or at least an intuitive understanding of those basics. If you have any questions or comments, send me an email. If you want to discuss working at Polymathian or want to know more information, shoot us an email to our careers email address. Thanks very much.
Thank you, Jackson. We'd like to give you the honorary UQCS mug.
Thank
So
you.
There we go. So,
Excellent. Thanks very much.
As Jackson said, Polymathian do have careers, and they do actually have part-time and casual positions available. So if you're interested, check out their careers website at polymathian.com/careers. Of course, shoot them an email. Coming up this week, we also have a Thursday night talk with the one and only Raggy. Raggy is, what's your talk called again?
Robots that run and dance.
There we go. Next week in the mid-semester break, we're actually doing laser tag. You can see it on Facebook called Pew Pew Laser Tag. Tickets are only $10, so arguably the cheapest laser tag you can get from a uni society on campus. So get your tickets now. And of course, AGM is coming up the following week, so week 10. Nominations are open for committee positions, so if you're interested, feel free to come speak to me or Kenton after. And yeah, cool. Pizza is, I think,
Yeah, pizza's here.
pizza's over in GP South, so if you want to make your way over, and yeah, cool. Thanks everybody.
Thanks.